Okay, so let's find out what's out there. How do we manufacture? How do we fabricate? Well, I said before that we can classify this in many different ways. One of them is looking at it from the perspective of, well, how many parts do you expect to make? Do you just need a few, or do you need to make this by the thousands? Okay, that's one taxonomy, one way of classifying. The way we're going to classify is another very traditional, very common way that you find, which is according to the physics of the process. In other words, how do you physically make the parts? Okay. So based on that, we have five different classifications here. We'll call them bulk formation. Okay. So putting material together in some net shape, and some of this is going to start, I hope, sounding very reminiscent of the way we've been building parts in SolidWorks. So we're going to do a full go around and return, to SolidWorks, once we have, this new manufacturing process knowledge in hand. Okay, that's not yet here. Okay, so let's continue. So bulk formation is a way of classifying processes, manufacturing processes. Bulk deformation. Okay, so we take some shape, some stock material, and we deform it to turn it into our net shape. Okay, material removal. So that's we hog out material from the part. Okay, the things that we do not want to have in there. So think in terms of extruded cuts, right? Features where we remove material from the part. We may want to do the opposite. We may want to join parts, and there could be very good reasons for doing that. It may be too difficult to hog out material versus just making two separate parts and finding a way to attach them together. Okay, so think of shapes that would not lend themselves to having a lot of material removed from a net shape, but rather where it would make more sense to put them together. Okay, so that's joining. And then finally we have finishing. So finishing is basically once the part is made, we may want to impart on it certain characteristics, either of precision or surface finish, etc., to make them fit a particular design purpose. Okay, so we'll talk about all these in turn. All right, let's begin our touring here with bulk formation. So there are the main processes. Now we're not going to be 100% exhaustive. We're going to be rather exhaustive, just basically a mile wide, inch deep. As for better or for worse, is in many ways the tenor of this course. Okay. So casting. Now casting can happen. Usually you hear of sand casting, metal casting. Okay. There's also investment casting that you may hear about, and others. Again, I'm not going to be rattling every single possibility here, but just to put a few words in your mind. Okay, molding. Okay, so molding, the king of molding is going to be injection molding. So that's more in the plastics side of things. Okay, powder metallurgy is there for completeness. Really, is one that would be unlikely to be used in the model and prototyping stages. Which is really one of the major emphases, of our exploration here. And then rapid prototyping, the almighty rapid prototyping, very, very well known. Okay, let's take a quick look at these. Just a few reference visuals. So the concept of casting is very simple. You liquefy the material, you pour it into a mold, then you let it solidify again. This can happen at the level of a metal, and it can happen at the level of a plastic as well. Okay, now obviously we're talking about vastly different temperatures, vastly different designs, for the nature of the mold, etc. Okay, but that's the basic principle. Okay, so there you saw some metal cast components, and here are some plastic cast or molded components. Okay, so in this case, you make the mold, and then out of the mold comes the part. Oftentimes these molds are reusable, so you may be able to use this process, for some parts, but this might or might not be suitable, depending on the part, for a high volume process. Sand casting, can be done on a high volume basis. Okay, now injection molding, that's one of the most ubiquitous manufacturing processes, for parts that we come in contact on a daily basis. It consists, of course, in melting the plastic and injecting it at very high pressure into a rather strong cavity, a rather strong mold, and you see an example of that there on the bottom right. Okay, so it takes quite a bit of effort, in fact, to machine these molds, but if they're made out of a sufficiently strong steel, they can be good for hundreds of thousands of parts. And there on the bottom left, you would see an assortment of typical injection molded parts. So a very traditional, very well developed, very standardized, and well known process. Okay, this is powder metallurgy here, so it's not nearly as common. Again, for in the prototyping realm, these tend to fit only particular geometries, and this consists. It's hard to tell from the picture, but this consists primarily of taking metal powder, compressing it, perhaps adding a binder to it, and then sintering it. Sintering is the word that we use for letting that powder fuse into a fully formed or a fully solid part. And again, you see some examples there. This has a tremendous application in the, for example, automotive parts. Again, this is not the type of process that would be at hand, for or easily at hand for prototyping purposes. Rapid prototyping. Well, this is, of course, a very, very relevant process. This is very much a brand new, 21st century technology. It's been traditionally dedicated or found, shall we say, in the realm of plastics, but it is now becoming more and more common in the realm of metals. Okay, so that's just starting to take off right now, but very well known, very ubiquitous for plastics. Several different processes. Some are based on fusion from powder beds of material, whether it be done with heat, so that would be, for example, selective laser sintering, or with a chemical binder, as which would be the case for the so-called 3D printing. You can also do it as an extrusion process, so that would be FDM, fused deposition modeling. You can also do it from impinging with a laser on a vat of resin, so that would be the case of stereolithography. And there are others yet. So this is a increasingly useful technology. In fact, more than that, it's actually quite approachable these days. You can buy your own rapid printers, rapid prototyping printers, most of them based on the fused deposition modeling or the extrusion process, which tends to be not necessarily the highest resolution, but certainly good for many parts, and using real materials such as ABS and others, nylon even. A lot of activity in this area, a lot of innovation. So by the time I finish this video lecture, there will be, or we won't be far away from new processes, new machines, new offerings, etc. So tremendous possibilities here, and a tremendous relevance to how we can design with this. Okay. Let's look at bulk deformation. So here we're going the other way. We're starting already from some stock material in here, and we're going to bash it into submission. This is also what's known as the heat and beat industry. So there's the big forging hammers, for example. So that actually forging is one of the common examples. Okay, rolling processes. This type of processes are made oftentimes to create the stock material that we purchase. So we talked about commercial off-the-shelf metals, for example, commercial off-the-shelf plastics. They come in bars, they come in sheets, ingots, in beams, in angles, in U-shape channels, etc. So these are the processes that will create these stock material shapes. Okay, extrusion is also a forming process. So that's, of course, in that case, we are actually shoving the material through a die to give it a constant cross section. So that has a direct parallel to our beloved extrusion in SolidWorks, parametric solid modeling. I also have in there vacuum forming, and this is a process more specific to plastics, where we start with the plastic sheet and then we impress upon it some manner of shape. Okay. Now there's also sheet metal in this category. Sheet metal, of course, will start with a thin sheet of steel, for example, and we will do a series of operations on them in order to create parts that themselves can be three-dimensional. Three-dimensional, I mean, having a significant three-dimensional shape, but oftentimes, they'll be planar. Sheet metal turns out to have a tremendous range of applications. Just open any computer, and you are going to find that the innards inside the casing, anything that's holding the whole show together, is some manner of sheet metal that has been subjected to various processes, and these are unique to this particular category. I list them there: stamping, bending, drawing, but there are very many others, again, with their own particular lingo. Okay, all right. So the picture there in the upper left, that is the quintessential forging method. So that's the hammer blow to a metal part that has been preheated. Of course, this takes us back to the days of smithing, when this is the way swords, would be made. And naturally, nowadays, this is done with very sophisticated machines, big hammers that come down with tremendous force, sometimes doing it in multiple operations, multiple stages, in order to give a final form to the part. This creates very tight, very, very strong parts. The strongest parts that you can get generally are done by forging. Okay? Down on the bottom left in there is a schematic of what would be a rolling process. Okay? So you can think of it as continuous forging. That's a way to think of it. And this can be done with hot parts, or it can also be done cold, and it'll, of course, impart different metallurgical characteristics to the end product. Okay? On the upper right in there, we see common extrusions, generally made out of aluminum, but not always. And this is, again, forcing the material through a die, and therefore creating a part with constant cross section. And we can relate to that, I'm certain, very, very well. And down there on the right, we're looking at a so-called break. And what this machine does is bend sheet metal or even shear sheet metal. So those are two uses for this type of equipment.